So the recording has also been started. And then we will continue with our agenda from the previous class. That is to do with statistical tests. So, and we will learn by example how to do and what to do. Okay. So this. So today we will start with the first example of statistical test, which is say sampling of data. Or basically reduction of background and so on and so forth. So what I mean by the sampling of data, okay. So I will talk about that you have two competing hypotheses. So we have uh, two hypotheses. I will call them H0 and H1. Okay. And looking at the data, we have to choose one over the other. Okay. So looking at a random data point, we have to choose one over the other. Yeah, so this is the idea basically. To give a concrete example, suppose you are trying to distinguish between electron and pion. Okay, so example is suppose you are trying to distinguish between say electron and pion. Okay, now this is a bad example that I have chosen. There are many ways to distinguish electron and pion quite unambiguously, but suppose you are trying to distinguish between them by looking at the ionization that they produce in a in a gas chamber. Okay, so what I mean is that so if you have a gas chamber, okay, with or any ionization chamber, so these kind of detectors are called ionization chambers. Which are usually filled with inert gases, okay, and with some electrode that I have not shown. And if you if a radioactive radiation, if a radiation falls into this chamber, then as it travels through it, it basically ionizes the gas inside it. Okay, so suppose it you so this is the entry point. So this is the entry phase, and you have this and this. These are kind of the length, the track length. So these are the like the tracks that you see uh, in a ionization chamber or a cloud chamber. So these kind of things actually leaves a track. Now, what does this track depend on? This track depends on the initial energy of the ionizing particle. So if the energy of the incident particle is above a certain threshold, it will start to ionize. So it is basically continuously colliding with the gas molecules, and as long as it has not lost its energy beyond the point where it fails to ionize the gas any further, it will continue to ionize those things. Ionize means it will knock off electron from the outer cells. Okay, and by looking at this. So this track length would be basically kind of a measurement of energy of a particle, and also it can reveal the identity of the particle. Okay. So the point is that both electron and pion can leave such track lengths. Okay. Now, so what you have to do is that, so once you see this track length, you do not know whether it's an electron or a pion. Okay. Now so after seeing a lot of events, now so you see basically a lot of events, how electrons and pions behave, and how uh, how their track lengths are statistically distributed. Then you make a decision on a new observation. So you observe such millions of such experiment, you have done millions of such experiment, when you know that it is only electrons that are coming. Okay. And you have also done millions of experiment where only pions are coming. Okay. And now you once you do the such millions of experiment where these electrons are coming, and you have found the distribution of this track length when the sample is almost purely an electron, and you have also constructed a distribution where the track length is purely made up of pion. Okay. So for convenience, I will call the H0 to be my electron hypothesis and H1 to be my pion hypothesis. Okay. So what you have done here is this. So suppose so in this direction you have the track length that I will denote by, let's say, T. Okay. And this is the distribution of the track length, which I call GT. Now the distribution of the track length, that means how you get this much of a track length with what probability, that gives you the distribution of a track of the track length. So suppose one of the distribution is like this. Okay. And I call this thing the distribution of track length given the incident particle is an electron. So this is the electron track length. How did you get this? So you have passed millions of electron through this ionization chamber, and then you have basically calculated the statistics. What is the statistical probabilities that this is true? Okay. And by the way, one thing I noticed that one of the student is not here. Who is that? Is Jerry. I think maybe he has tried to join and could not join. So can anyone check with him if that is the case, and let me know if
Yes,
that is
yes.
the, yeah. So anyway, uh, so this is how you get the distribution of track length given it is an electron. And similarly, you have obtained another distribution of track length if the particle, incident particle, is a pion. Okay. And suppose the distribution is like this. Okay. So this I call the distribution of track length provided it's a pion. Okay. Did everyone understand how I get these plots? Okay. So I have a pure sample of electron. Somehow I train my detector in this way. So if the sample is purely made up of electron, my distribution of track lengths will be like this. And if my particles are purely pions, then distribution of track length is like this. Now the question I ask is that, suppose now you are given now the detector you say is ready. So I have done enough training with millions of data, millions of data, and now I place the detector in an unknown source, and that unknown radiation comes, and I get a track length of this. Now, based on this information, that the plots that I have to conclude, I have to make a decision now that whether this red track length is an electron or a pion. Does everyone understand this concept here? Okay. Everyone is with me. If at this stage there is a problem, you should tell me now. Okay. Because these will get increasingly complicated. All right.
Sir, how we get this pion distribution? Means by just estimation, hypothetical.
Uh, Depends. If you have the luxury to do experiments with pion, suppose you know how to produce pure pions. Okay, you know a source that only produces pions. So you place the detector in front of it, and millions of pions basically pass through these chambers. From that, you derive the statistical distribution of track lengths given it's a pion.
Okay, sir.
Okay. And if you do not have the luxury to do experiments, you usually rely on Monte Carlo. All right. Okay. So, anything else? All right. Now, so the idea, essential idea, how to do it. Okay. So, it depends on making a decision. Okay. So you have to make a decision for this unknown. So this is my unknown particle. This is my unknown track. Okay, length. So, and I have to assign. So uh, it is an electron or a pion. Okay, so this is what I have to decide. So the way to do it is to choose a cutoff t, cutoff value of t. Okay, so this so suppose, so this I call t equals t cut. Okay, so this is you choose a cut. So this, what I will be describing, is popularly known as cut based analysis, if you prefer a fancy term, but you will get the essential idea here, that how to distinguish between two hypotheses. So now, how to choose this T card? That's a different problem. Okay, that's a different problem altogether. How I choose this T card? But suppose from this kind of visual separation of those two distribution, if I choose a T card like this, and I notice that if my unknown track length, my unknown track length is around here, so this is my unknown track length. Okay, then it's kind of more likely to be a pion than an electron. And if this unknown track length is below this cutoff point, then it is more likely to be an electron than a pion. Okay, so this is my this is my T cut. Okay, so I have chosen it apparently arbitrarily as of now, but there is certain way you can choose that, but you get the essential point. So if the peaks of the two distributions are well separated, two types of distribution are well separated, then you can choose a suitable cut value of the variable in question, of the random. Here t is the random variable, so you can choose a cut value of the random variable in the question. So if you so suppose if e is my h0, okay, then and then if the observed value of t is greater than t cut, then you reject h0 in favor of h1. Okay, and if this t, if the observed t is below this t cut, then you accept h0 and you reject h1. You reject h1 in favor of h0. Okay. Now, of course, since these are all statistical distribution, these kind of decisions are prone to error. Okay, so there is a finite possibility that even if your t value is greater than t cut, there is a finite possibility that this can still be coming from the electron, that still be H0 is true. Okay. Now, so remember, if T is greater than T cut, you are concluding that the unknown particle in question is pion. But there is a finite probability that you might be wrong. Okay, so that means you are rejecting H0 even when H0 is true. Then what is the probability of that? So the probability of that, probability of making that error, which I call, let's say, alpha. So alpha is basically t cut to infinity in this case. Okay, and this is g t e here. I mean, e is H0. This is dt. Okay, so this kind of gives you. So this is sometimes called the type 1 error. Okay, so that means um, this is the probability of uh, rejecting H0 even when it is true. All right. Okay. So this I will call the probability of rejecting H0 even when it is true. Now the opposite is the type 2 error. So the opposite error will be type 2 error. So beta is equals to uh, minus infinity to t cut. Now here you will have g t pi dt. Okay, so this is usually called type 2 error. So this is probability of accepting H0 even when the alternative hypothesis is true. Okay, so so it is the probability of accepting H0 even when an alternative hypothesis.
So
Yes.
it will be H0 or H 0 because in the first case H1 is true. You have taken the pion to be.
Pi is H1. Yes.
So in the first case it will be H1 or H2.
What here?
Here alpha will be probability of rejecting H1 if even though it's true now, or is it universal? Not clear.
No. Probability of rejecting H0 even when it is true. So you have a T cut here, and based on this T cut, you are accepting the YOLO thing. You are concluding that the YOLO one is true. But there is a finite probability because the tail of this uh, distribution uh, is because of the tail of the green distribution. Even when the green is true, you can falsely be misled to conclude that yellow is true even when actually green is true. So what is the probability that you get a t value greater than t cut even when your green is true? So that is the error I am making. That is the error I'm saying by alpha.
Okay, okay.
Okay. And the opposite one is called beta. Okay, so you can think of these things. So this is basically a false negative. Okay, and this is a false positive. Okay, and sometimes the other alternative names are also used. So this alpha is sometimes called the significance level of a test. significance level of the test, and this beta is sometimes called the power of the statistical test. Okay. Now you can try and see how can I optimize the choice of this T cut. Okay. Now, of course, your ideal choice will be when both this alpha and beta are as close to zero as practically possible, so that you do not make any error whatsoever. So to reduce alpha, you will be tempted to move T, this T cut, towards the right, so that the tail, the area under the tail is reduced. But the price you pay is that you increase then this area which reflects my beta. Okay? So this area reflects your beta, and this area reflects your alpha. Okay. So often you have to make a compromise, and you have to settle down to an optimal value of T cut, and that optimal value will be chosen. Like, there is no unique way of choosing an optimal value for T cut, but it is a compromise, and it's where you will make a compromise and where not will depend on the problem in hand. Okay. But the essential idea is that the essential idea for the cut based analysis is that you have to choose a value of the T cut, and uh, that will and if it is towards the right, then you accept the hypothesis, and if it is towards the left, then you reject the hypothesis. Okay. Now there are certain fine prints that you need to note down here. Okay. So this T, in this case the example is the track length. uh, it is itself uh, plays the role of the thing that distinguishes between two hypotheses. So the T is, I will come to those examples. Okay. So this T, which is, I will call it to be test statistic. Okay. No S, remember. So it's called a test statistic. So it's a construction. So it's a construction. Okay. It can be an artificial construction. Um, it's a construction from the data. Then it's a function. It's a function of the observed data. Okay. And what kind of function it needs to be, uh, that again will be a question of choice that I will discuss a bit in more detail. Now, the whole point of constructing a test statistic, the motivation of constructing this test statistic as a function of the observed data, such that uh, my two hypotheses, this H0 and H1, become separated when I look at the distribution in terms of T. So the goal of this construction is that, so the goal of this construction is that the distribution in terms of T in terms of t can distinguish um, H0 and H1 very well. Okay, so this is the, and I will call this construction to test statistic. The example I give you is a super simple one. So notice that the data you observe is an ionization length. Okay, let me call it to be x. Okay, so the because the ionization length, there is only a single quantity that you are measuring, that's the ionization length inside the detector. Okay, so let me call it x. Okay, so this is my ionization length. Okay. Hmm. And here, basically, you are constructing this t is essentially x. So this is a function, this is a trivial function. The t is essentially x. And in terms of this t, you have this distribution. But suppose someone had chosen, let's say, this is just an example. Suppose someone has chosen, let's say, t equals x to the power 3.5 for some reason. Okay, so let's say that t prime, I call it t prime to distinguish from this t. So t prime equals x to the power 3.5, or x to the power 3.5 plus 2x square. Okay, more complicated stuff, and that is made from this x. Okay, and in terms of this t prime, so you can again, now you know the, if you change your variable, then how, so in terms of this t prime, you will have new distribution g of t prime. So you will have a g of t prime if electron is true. Okay, so suppose this is my g of t prime if electron is true, and let's say this is my g of t prime if my pion is true. Okay, in terms of this new test statistic. Okay, now you notice that if you compare with the previous figure, okay, then in the plane of t prime, these two hypotheses, that whether it's an electron or it's a pion, it is even better separated. Okay, so so if this is true, then you will prefer this test statistic over this one, over t. Okay, so the whole point of constructing a suitable test statistic is that whether it can distinguish uh, one hypothesis from the other, and the test statistic basically so the construction of an optimal test statistic is itself a kind of an interesting point of research. Okay, and for a given problem, you might want to adopt a very particular strategy on how we will construct a test statistic. I will discuss in some superficial detail about this interesting problem and how to do these things. But I have started with a simplified problem where you measure only one quantity. This is only the ionization length, and you are considering that this itself is my test statistic, and you have two distribution, and you choose a cut and you try to analyze your data. Okay, so we will proceed with this simple example where the test statistics somehow has already been constructed, that is t equals x, and I am trying to distinguish between electron and pion. Okay, let's see what happens then I will come to the question on how to construct a test statistic. Okay, so for now you should accept that this is my test statistic, and based on this I am going to distinguish between electron and pion. All right, there is another interesting point to note here. Okay, like what kind of hypothesis I am working with. All right, so the hypothesis I am working with here are called simple hypothesis. What do I mean by that? So if this distribution, that is a distribution in terms of my test statistic for a given hypothesis, is completely determined. Okay, so if I tell you that my hypothesis, the given hypothesis is is electron. So suppose there is only electron that is entering my chamber here, then there is no other unknown things in my distribution. So I can know quite unambiguously by doing experiment how this distribution should look like. There is no additional parameter. All right, it does not depend on any other additional parameter. It is completely determined. So this kind of hypothesis are called simple hypothesis, where there is no parametric dependence on anything. Okay, and if my hypothesis would depend on any additional parameter, then of course I do not know this green curve uniquely. Okay, then I cannot make such a distinction. So first I need to fix the parameter. That's a different kind of problem, a parameter estimation. And those kind of hypotheses where this distribution, the distribution of the statistic depends on external parameters that are unknown, whose true value will actually forever be unknown, those will be called compound hypothesis. And as I told you in the previous lecture, so dealing with those kind of hypotheses is a entirely different type of problem. That's the problem of parameter estimation. Okay. So now, basically, if I have chosen my test statistics, so the form of the test statistic, that is the first choice that comes into being. There are two choices that I am making: the functional form of the test statistic, and then what is the optimal cut value for the test statistic. Okay, there are two choices that I am making. Okay, so suppose I am accepting that this is my choice of test statistics for one reason or other. Now let us try to figure out how will I choose my t cut. Uh, the choice of t cut will depend on what kind of things you are looking at, and what are your priorities. For example, you can define the efficiency of selection. Okay, so you can define the selection efficiencies. Okay, now first, so this is the electron selection efficiency, that is minus infinity to t cut. Okay, g t given e dt, which is nothing but 1 minus alpha, if you look at the definition of alpha. So this I will call my electron selection efficiency. And then there is another thing that you can define, which is called epsilon pi, then minus infinity to t cut, this is g t pi dt. So this is simply beta, and this is basically pion rejection efficiency. Now you see there is a basis for choosing your t cut. So what does this electron selection efficiency mean? So remember, all the electrons that actually fall that come to your detector here, okay, are described by this area under the green curve, the full green curve. All right, but since you have placed a cut here, that means you are only accepting those electrons which lie below t cut, which lie below this t cut. Okay, so just by, so remember, to if you want to ideally, you want to do an experiment, suppose you are trying to measure some properties of the electron. Okay, then you want to accept as many electron as possible. All right, so if you want to accept all electrons, then this your T cut should be at infinity. You should include everything. But then there is a problem that you are including pions as well. There are too many pions to deal with. So that's why you are forced to place a cut. And whenever you are placing this cut, you are accepting fewer electrons than the total number of electrons. So the fraction of electrons that you are accepting because of this T cut is defined as your electron selection efficiency. So that is this. This is 1 minus alpha. So alpha is the thing that you are chopping off. You are basically rejecting those electrons because you do not want your pion contamination. And then the opposite is again true. It's the pion rejection efficiency. That is, by allowing this T cut, by how much pion are you allowing to contaminate your result. Now, depending on the nature of the data analysis, or the nature of the experiment you want, if you if your data analysis demand that you need a sample of electron as pure as possible, so it does not depend on the total number of the electron so much as does it depend on the purity of the electron. So suppose you have 100 electrons, okay, so your data analysis demands that even if you accept only 20 of them, make sure that all the 20 of those electrons are just electrons. There are nothing else. So I want a high purity of the sample. Then you want to focus more on beta than alpha. Then your primary goal would be to reduce beta, and you will not pay so much attention on alpha. On the other hand, if your experiment or your and nature of data analysis is such that it relies on the number of statistics, the sample size, okay, so you want to accept as many electrons as possible, even if you have to make compromises with contamination, that is still okay, but you want to reduce, let's say, the statistical error in your measurements, then you want your sample size to be large, and in that and in that kind of experiment, ideally you would want to increase your efficiency of selection, okay, so that you will want to more reduce alpha, even when you have to make some degree of compromise with beta. So you understand the 2 points that you are trying to measure, okay. All right. Now, actually, in fact, there is one added degree of so basically there is one extra parameter that usually enters your study, that is the relative fraction of electrons and pions, okay. So suppose you are doing this experiment in a cosmic rays, okay. So in cosmic rays, basically in a typical cosmic ray, the relative frequencies of electrons and pions are known, okay. So suppose for 10 electrons you get 1 pion, okay. So these are known, okay. Then not only the distribution is important, not only the distribution of this ionization lengths are important, but you also need to include the probability that one electron will hit this chamber, okay. So if it is much more likely that an electron will hit this chamber than a pion, then these pion events will be extremely rare, okay. Then so that is kind of the Bayesian priors actually. So if you think in terms of Bayesian statistics, that is the kind of the prior probabilities, that how frequent are pions at the first place, then you will worry about this distribution, okay. So you should ideally add to the kind of the prior fractions of electron and pion. And suppose I denote so I call this prior fractions of electron and pions, and these I denote by AE and A pi, so that AE plus A pi equals to 1. So this is depends on what kind of sample you are working with. So you are working with a sample where the relative abundances of pion and electron are known a priori, if it is, let's say, cosmic group. So in your sample, the relative abundances of E and pi are known. Okay. Now, so now basically you can construct an interesting probability distribution that so you call it probability of finding t given a value of ae. Okay, that will be basically, first of all, the probability of finding t given it's an electron times the probability of finding an electron, so g times t, plus uh, probability of finding t given it's a pion times the probability of finding a pion, right? So think about it like this. So you are trying to find the probability of finding ionization length, that is t. Ionization length is t. Now ionization length, this ionization length come from two sources. So electron can produce this ionization length. Suppose it's 2 centimeter. This 2 centimeter is too large. Let's say it's 2 millimeter. Okay, so this T is, let's say, 2 millimeter. So electron can produce a 2 millimeter ionization length, and pion can also produce this 2 millimeter ionization length. Okay. So first of all, what is the probability that an electron will produce this 2 millimeter ionization length times the probability of finding electron itself in the sample? Okay, plus, okay, the probability that pion will produce that length times the probability of finding pion itself. All right. Okay. So now, so remember, now you have an extra parameter AE here. Okay. So, this AE, if it is known, then it will affect your, it will affect your total sample. Basically, it will affect your the accepted number of electrons, and you want to increase the that number. Okay, so what you can do is that you can try to figure out, you can try to define something called uh, how did I define this? Let's see. All right, maybe this is something. So you try to define the purity of the sample. So you define like this. So the purity of the electron sample will be, so it will be the number of electrons with t less than t cut divided by the number of total particles with t less than t cut. Okay. Remember, your detector only accepts particles when t is less than t cut, right? So that it will accept electron as well as pion. Now I am interested in the in the ratio, that how many electrons do I get for this t less than t cut compared to my total number of particles with t less than t cut. Okay, so that is kind of easy to calculate. So the quantity on top will be minus infinity to t cut. Okay, then the probability of finding an electron uh, with value ionization value T. Okay, so that is GT given an electron times the probability that I will get an electron. Okay, so that is my AE times DT in a sample. Okay, divided by rather, okay, that is again minus infinity to T cut. Okay, that is the integration of this f that I denoted. So this is basically the probability that I will get an ionization length of T no matter what. Okay, so this is the probability that we will get T no matter whether it's an electron or a pion. Okay, no matter what, that I will get this value of T. Okay, so in the denominator basically you integrate that quantity because that actually gives you the total number of particles that has been accepted here. Okay, so this is the probability of electron only, and this is the total probability. And in terms of practical quantities, remember on top that is the number of electrons with T less than T cut. So if the total number of particles are denoted by n total, then only AE times n total is the number of electrons. So AE times n total is the total number of electrons. So this is the NE equivalent to total number of electrons. All right. And since my electron selection efficiency is epsilon E, that can be determined by this. This is my electron selection efficiency. Then epsilon E times this is the total number of accepted electrons with T less than T cut. Okay. And this is divided by n accepted. So the total number of accepted particles with T less than T cut. So this is the total number of accepted particles. Okay, so this is basically if you want, so this is equivalent to epsilon E n E plus epsilon pi n pi. Okay, if, that is the thing. So this you can measure experimentally. So the epsilon E is something that you are fitting, that you are choosing here. So epsilon is something that depends on your T cut. Okay? So epsilon E is something that depends on your T cut. And this AE is known, and this N total is also known depending on the sources. If you know the flux of particles that are coming through your detector, okay, the cosmic ray flux is known, and this N total is also known. Then what you can try to do, so the only thing that you can tune here is this epsilon E, and these numbers you have measured from experiments. Then you can try to choose a T cut in such a way such that the purity of this electron sample is maximized. Okay, so so you choose, so you may want to choose T cut in such a way so that the purity of the sample is maximized. Okay. Remember, so here this is a tricky business. because as you try to reduce this epsilon, so remember you might want to increase this epsilon e, right? So you might say that since this expression depends on just epsilon e, if I try to maximize this epsilon e, make it 1, and then I have maximized it. That is not true, because as you want to increase this epsilon e, there is something in the denominator epsilon pi that also gets increased. Okay, so you cannot just monotonically increase this epsilon e without affecting this epsilon pi, because epsilon pi, if you remember, it is also increased as you move your t cut towards the right. Okay, so there is an optimal place to move this t cut and place it in an optimal position, such that if I am interested in the purity of the sample, then this purity will be maximized, and then you will find a value of t cut. Okay, so lesson learned. If you are trying to distinguish between two hypotheses, let's say H0 and H1, first of all, you have to construct a test statistic. Okay, I have not discussed how to construct the test statistic, but given the fact that you have constructed a test statistic in a certain way, the number two job is to choose a cut on that statistic, on the test statistic. Okay? And how will you choose a cut will depend on the nature of the problem that you are working on. I gave you one example where you may want to choose your cut on the test statistic in such a way so that the purity of the sample is maximized, and that is kind of um, it's kind of a good way to figure out what is your cut. Okay, so I will pause for a brief moment here, and I will see if there are questions or things are clear so far. Is everything clear so far?
Yes, sir.
Hello, sir.
Yes.
Sir, while you defining the ionization track and the particle the track length,
Yes.
you are saying t equal to x, and for optimization, you are saying we have to design t in such a way that it will optimize t prime x is t is a function of x.
Yes.
Can you again distinguish between track length and ionization length with respect to that t equal to x, and t is a function of x?
Uh, I mean, I meant track length and ionization length in the same sense. So they are the same thing, first of all. Now,
Okay.
T is a different thing. You can choose it to be just the ionization length, but it can be a more complicated function of that measured quantity. Uh, if it
In another different situation, it may be different, or
Yes,
in your example, it is same.
in this example, it is same,
Okay.
but in this uh, it is different. So it is a this function, this weird looking function, and maybe this.
And
So,
we have to
so
decide how t will be a function of x. This is the optimization technique.
yeah, that is the optimization technique. Okay, there are
Okay.
two kinds of optimization. First, how to choose t, and then given a t, how will you choose a cut?
Okay. Yes.
Okay.
Yes.
Uh, so remember, if you complicate this function, then your computational complication are also increasing, and you
Yes.
have
Yes. Yes.
only a finite amount of only a finite amount of computing power. So it is more often it is like if your computational power is finite, then it is recommended that you choose a simple test statistic so that your computation is faster, and then you optimize your cut. Okay.
Okay.
So you have to, yeah, we will come to that. We will come to that. All right. Anything else?
Sir, one more point. While you are defining f of t, f a e, you are saying this is the probability of finding t, no matter what is. But you are looking at the probability of electron. You are writing a of e.
Yes.
Just because you are interested in finding electron, or it should be both a and a pi.
I mean, this quantity I defined to later define the purity of the sample. The purity of the sample is defined as the ratio of number of electrons over the total number of particles. Okay.
In fast region, so that you are writing AFE, or what? If you are comparing with the curves, two curves we have drawn fastly,
Yeah, yeah. In the first.
you are interested in the fast region, so that
Yes.
okay,
Yes. I mean that for a particular choice of the test statistic.
okay, yes.
Okay. So remember there are two. As I told you, there are two things in the test statistic. One is the structure of the test statistics, and then what is the cut on the test statistic. Okay.
Okay.
All right. Now I will move to yes.
Should the selection efficiencies also be a function of the relative abundancy?
No, absolutely not. So the selection efficiency are independent of the relative abundances. The selection efficiency are only dependent on this distribution of the test statistic, and test statistic are obtained by basically this is the data training by training your computer in a sense in the ideal case here training your detector. So remember when I am constructing these things, no matter how I am finding 1 million electron and I am finding 1 million pions. So first I shoot 1 million electrons in this detector and see how it behaves, and then I plot this. Then I shoot 1 million pion into this and I see how it behaves. Okay, this is essentially your Monte Carlo training. You understand the point here?
Yeah.
Okay. So these distribution do not depend on the relative abundances. Now, since now my detector is trained how to handle this, it knows how things are distributed. Now, looking at an unknown track length, I would be able to conclude whether I am looking at an electron or a pion. Okay.
Yeah.
All right. Okay. Now, I move to the second part. By the way, do you need a break? I forgot to ask. Is it dragging too long? If you want a break, I can give you a break. Otherwise, I can continue.
Continue, sir.
Okay. So now I come to the important part of constructing a test statistic. So I will I will restrict myself to mostly a semi-qualitative description, because some of you might already know more than me regarding this without knowing that you know more than me. Okay, so this is a semi-qualitative discussion, and people who already know more than me about this may help me and the other participants to understand better. Okay. All right. So what do I mean by that? Remember, in the previous example, which was one of the simplest example of data sampling, we are measuring only one quantity x, and we are looking at the distribution the distribution in terms of this x or a function of x. Now, in practice, we basically measure many different properties. Okay. For example, in addition to x, in addition to the ionization length, you also measure the energy of the energy deposited in the chamber in that thing. Okay, so then you will have a two-dimensional plot. Okay, and I think some people are bored hearing about particle physics experiments. So let me try to make it more general by using the example of this fish that I was giving in the previous one. Okay, basically, suppose you are measuring now two properties. One is, let's say, x1, another is x2. Both of them are data. Remember, this is not a statistical distribution, this is data. All right. Now, so this is a multi-dimensional discussion here, multi-dimensional measurement here. Suppose, so in that fishery, you are measuring, suppose, the length of the fish and let's say the width of the fish. Okay, so let's say here the average length of the fish, and let's say here it's the width of the fish. Okay, and for particle physics you can think about this is your ionization length, and this is basically energy. Basically two different quantities that you are measuring, and you have two types of hypothesis. This means two types of objects. In the case of the fish example, suppose you have hilsa and rohu, and then you in the particle physics example you have electron and pion. Okay, again, first job what you have to do is to first find a training data. By training data means that you run your experiment under controlled environment. Okay, so what I said in this earlier example. Okay, so remember I told you that first you send millions of if you send millions of electrons first and millions of pions first, so that is your training data. Okay, so that is the data based on which you are training your computer or things like that. So first you have to do something like that. So remember, in the case of this fishery, there was one guy who was sorting this hilsa and the rohu manually. Okay, and every time he picks up a hilsa, he puts a yellow cross. Okay, uh, he measures the length and the width, and in this plane it is represented by this yellow cross. Okay, and now another yellow cross, now another yellow cross. So this is the hilsa data, or maybe this is the electron ones in the particle physics. Okay, so this is how you get the picture. So these are all my data. This is my scattered thing. Okay, I'm not sure if this is how it looks, but suppose it looks like this. Okay, now he also, when he picks up a rohu, he places let's say bluish kind of circle. Yes, suppose. Okay, so this is my bluish kind of circle. Okay, and now this is what I have got. So this is the raw training data that I have got. I have measured many such points, and I have this two-dimensional plot. Okay, now I have an unknown thing, let's say right over here. Okay, so after I have found my this training data, then I catch a random fish with my eyes closed, I do not see, and I see in this two-dimensional plane of the data it is placed here, and I have to conclude whether it's a hilsa or a rohu. Do you understand the problem? It's a straightforward generalization of the problem in the case of multi-dimensional data. All right. Now, This is the thing here. Remember, so what you so how will you distinguish between now this yellow and the blue points? You want to do a cart-based analysis. The simplest thing that you can do, that you can put a cart on each of the variables on x1 and x2, and you do a cart-based analysis. Okay, so remember, so the first option that I am giving you, so you do something like this. Suppose you put a cart so this is, you call it x1 cart, and this you call to be your x2 cart. Okay, and you say that if my data is below both these carts, I accept that these are my Rohu fish. Okay, these are my blue points are more likely. And if it is beyond this thing, then these are my Hilsa fish. Okay. Now, this is a pretty good way of saying this, like without doing anything, without just placing cart at each and every variable, without just doing anything. Okay. But the question is, can you do better? You automatically notice, okay, so this is the way I have drawn this picture. It kind of gives you this intuition. So this is what I am trying to get here. So it gives the intuition that you can do even better. Instead of putting individual cards on the data, if you can draw kind of an imaginary line through these points, let's say a straight line like this. For the beginning, I am considering a straight line. Okay, and you now say that the points which are on this side of the straight line are mostly yellow kind of points, mostly Hilsa, and the points that are on this side of the thing are mostly blue points, that is, those are mostly row. Okay, and you know how the equation of the straight line should be, right? So the equation of this straight line, if I am allowed to write, so I construct a t, let's say, as a function of x1 x2, that is a1 x1 plus a2 x2. Okay, then so this a1 x1 plus a2 x2 gives a straight line. A1 x1 plus a2 x2 is a constant. This is a straight line in this plane. Okay, for different values a1 and x1. So these are parameters to be determined. So remember, a particular value of t, so if I fix a1 and a2, then the different values of t takes me to different parallel set of x line straight line. For example, for now I will fix this a1 to plus 2 and a2 to minus 3. This is an example. And suppose this t and the t value is, let's say, 9. Okay, and so this value, this plus 2 and minus 3, this plus 2 and minus 3 values of a1 and a2, and with this t value at 9 gives me this white straight line. So this set of values gives me this white straight line. Okay, this is my white straight line here. Now, remember, if I only change the value of t without changing the value of a1 and a2, notice again, if I only change the value of t without changing the value of a1 and a2, I am basically parallelly shifting the straight line over here or there. Okay, so I am basically parallelly shifting the straight line along this. So my job is to fix this straight line at a certain point. That is my t cart. So this, the white straight line is my t cart. So this t cart, first of all, gives me the optimal separation. Okay, so on the right I will get yellow, on the left I will get blue. Okay, so remember, I know the distribution in terms of x1 and x2. From this point I can conclude about so from this data, so from these data I can get the probability distribution. Let's say I denoted by G as, let's say G x1 x2 given H0 is true, and G x1, the combined PDF of the data I can get from this. Okay, now if I define this T to be this a1 x1 plus a2 x2 with a1 equals plus 2 and a2 equals minus 3. For this moment, just accept that someone has told me that this a1 equals plus 2 and a2 equals minus 3. Okay, for this moment just accept that someone has told me this a1 equals plus 2 and a2 equals minus 3. Then if I define my t as a function of these x1 and x2, then I can convert these two PDFs in terms of the distribution of the test statistic. So this is my test statistic, and I am converting these simulated events. These are my simulated PDFs now. So I'm now converting this into G of t given H0 is true, and G of t given H1 is true. Okay, so you can convert this using this definition. You know how to, if you change the variables from x1 x2 to now t, this t is given by this, the same as the previous class, then you can convert this into gth0 and gth1. All right, now this t is a single test statistic now. So t is designed such a way, you already notice that this t is more efficient. If I construct such a test statistic like this straight line here, then this is more efficient than this box kind of separation. I can separate my data more efficiently using this kind of thing rather than using this kind of thing. All right, then you can now basically try and plot this GTH0 and GTH1, right? So you again have now the same situation. You are led to the same situation. So once you have uh, mm, configured this, so this is T and this is, let's say, GT, and then one will have uh, like this. So this is my G at TH0, and then the other one is my, let's say, this is my GTH1. And again, what you do is you try to figure out an optimal cut. So this is again T equals T cut. Okay, so again, even if your problem is a multi-dimensional one, if you want, you can reduce to a one-dimensional problem like this one over here, just by wisely choosing a test statistic. Okay, so now you choose a t equals t cut, provided someone has told you the values of this a1 and a2. Okay, and this t equals t cut, so basically where to place this white straight line so that your data separation become optimal, and again you apply your rules of purity and something to decide where you want to put your t cut. Okay, so first of all, again I will pause for a moment here, and let me know if you have understood this point. Even if you have multidimensional data, you can reduce it to a one-dimensional problem by choosing a test statistic. And of course, you are not compelled to choose only one test statistic. You can construct multiple test statistic, and again you can apply multiple cuts. But in this simplistic example, the way I have drawn my data, maybe one test statistic is enough to distinguish between my data. So do you understand my point here? How can you reduce? Now the concept of test statistic is clear. Any question?
Sir,
Yeah.
then this complication will be how to determine this parameter, means how to find the relation between two variables or more variables. If we have to find
This
some
A1
test.
and A2.
Yeah, yes.
Yes, I'm coming to that. Right. Anything else about the conceptual points? Everything is clear, right? Okay. Now, all right. So, if assuming that these are clear, then the thing, as Amarendra pointed out, first of all, how we choose the form of the test statistics and how you determine this coefficient A1 and A2. Okay, the value of this t cart can be optimized just by using the kind of experiments that you are doing, and then how we construct this test statistic. Here you see that I have constructed a test statistic that depends on the first power of x1 and x2. Okay, and this is a choice. Nobody told me to do so. I looked at the data. Okay, I saw the data and I got a feeling that a linear test statistic might be good enough. Okay, then so then what I have to do is to choose this A1 and A2 wisely. Now remember, what does this A1 and A2 do? So suppose you choose a constant value of t, so let's say 9, and tune your A1 and A2. So this basically changes your slope of this thing. So about a certain point, this straight line a bit rotates either in this direction. So it so this straight line, which color should I choose here? Maybe the straight one. The straight line might be this or this or this. You get the idea, right? So this is the straight line. This is basically by choosing A1 and A2, you are basically rotating the straight line. So first you decide what is the optimal orientation of the straight line so that your data are well separated. Okay, so that your data were like so that your hypotheses are well separated. See, now I am moving towards constructing a test statistic. Okay, before choosing a t cart, before even I go and choose a value of t cart, I first try and choose my test statistic by, you see, I want to choose my test statistic, and visually I am basically kind of rotating this straight line, like try and like fiddle and basically try to fine tune which is the optimal orientation of the straight line that separates my data very well. Okay, and that is obtained by tuning A1 and A2. Now, what kind of mathematical consideration I am going to need so that my test statistic is optimally chosen? Okay, and remember, I have chosen it to be depending on only the first power of x1 and x2, and this particular choice, when your test statistic depend only on the first power of your random data points, of your like random variables, these are called the linear test statistic. Okay, so I will mostly focus on this simple example because this is something that I want to I can do analytically. So linear test statistic. Okay, so the linear test statistic means, so if you have n number of data points, so that is your basically tx. So this x is basically a vector. So this x is basically your x1, x2, blah 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 up to xn if you have n number of data points, and that in here is I equals 1 to n ai xi. So that is the general form of the test statistic that you have seen. For n equals to 2, you have that thing. And I will write this in a fancy form. So I will call it the A vector transpose and x vector. Again, see, if x is like this, then of course your A will be kind of a column vector, A1, blah, 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 to AN. If you take the transpose, you get a row matrix and you get this thing. Okay, so this is a convenient way of writing this thing. All right. Now, basically, since you already know the training data, so you already know this training data. So this is your gx1 x2 h0. Rather, I would like to change the names, because G is the name I reserved for my test statistic, and for data I will call it just F. Okay. So the probability distribution PDF of the test statistic, I reserve the G symbol for that. The F symbol in general, any PDF that is associated with the data. Okay. So basically, my job is to figure out how efficient is my test statistic in separating out H0 and H1. The more they are separated, these peaks are separated, uh, uh, the more efficient those test statistic will be. All right. So first of all, the mean and the covariance matrix, I would assume that it can be obtained from my test PDFs. Okay, so the mu, so the so this mu k I. Okay, so this is the mean value of xi for kth hypothesis. Let me do it in this way. Okay, so this is integration of xi, that is f x given hk is true. Remember, this f x hk is similar to this. Okay, for k equals 0 or 1. Okay, so these are the distributions that you get from this data. Okay. So if this is your fx hk, and this is dx1 up to dxn. All right. So again, remember, k equals either 0 or 1. So these are the two hypotheses. Let me not use k here. Let me use alpha, so that you do not confuse between the Roman and the. So the I, the Roman alphabet denotes my data, and the Greek alphabet denotes my hypothesis. So alpha equals 0 or 1. Okay, I have two hypotheses here. Okay. And similarly, the covariance matrix, this is V alpha. Okay, and the ijth element of that would be given by, similarly, uh, this is x minus mu alpha I. Okay, so this is my mu alpha I times x minus mu alpha j f x h alpha, again dx1 up to dxn. So these two things I already know. Okay. Now, then, given this, again using the transformation of variable, I can go to this GTK, GTH0 and GTH1. Okay, so I can convert this to my GTH0 and GTH1. So suppose after you convert this to G, this distribution to G, so in the tau space now, so now, sorry, in the T space, the T space means in the space of the test statistics, that is the renewed variable. This is the new variable that you have defined in this thing. The average, so the average or the mean, let's say, mean will look like, that is, I will denote by tau k, and that is basically average of T, G, sorry, not tau k, let's say tau alpha, GT given H alpha is true dt. Okay, so this is the new thing. And how does it look in this new space? It is equivalent to A transpose vector, then mu alpha vector. Okay. What do I mean by this? Remember, if you define a new variable, this is my new variable in terms of the old variable, then the mean of the new variable in terms of the mean of the new, old variables are that in this functional form, if you just substitute the mean values of the old variables, then you get the mean of the new variable. Nothing else, right? This is the lesson from our last lecture. Okay, this is a new variable, and these are my old variables. You just replace the old variables by their means, and you get the mean like this. Yeah, this is my tau alpha for alpha. So this is again alpha equals either 0 or 1. Okay, so for the H0, the mu is tau, the mean is tau 0, and for H1, the mu is tau 1. All right. And similarly, you have also learned that the variance in the new space. So this I call sigma alpha square. Okay, the capital sigma. So this is basically integration of t minus tau alpha whole square. Okay, it's g t given h alpha is true dt. So this is basically a similarity transformation uh, in terms of the coefficient matrix, and the coefficient matrix is A. So the new in the new basis, the thing will be, which is A transpose times the matrix V alpha, this old matrix V alpha, times A. Okay, so this is my new sigma square. All right. So this is the mean and the sigma alpha square. Okay. Now, what does this mean? What does this mean in terms of the figure? Okay. So remember, the mean of a distribution basically is located very near to the very near to this thing. So this, suppose I denote by tau 0. This is my tau 0. This is the mean of the GTH0 distribution, right? According to my definition here, this tau alpha, which is this tau 0, is over there. And this tau 1, similarly, is over here. Okay. Now, again, the width are also given by the standard deviation. So what is this sigma alpha square? The sigma 1 square and sigma 2 square. What are those? So this sigma 1 square, so this is kind of my sigma 1. So the mode is the width, the mode is this thing. And this thing, apparently this width is a measurement of sigma 0. Okay. So this is a kind of a measure of sigma 0. All right. Now, try to quantify now. When will the separation between these two PDFs in terms of the test statistic, the test statistic are maximized? When is the separation? How can I quantify the separation between these two test statistics? All right. The answer is, if the separation between the means are large, if these two peaks are separated enough, that means I am trying to maximize the separation between tau 0 and tau 1. Okay, maximize the magnitude of the separation, the difference in tau 0 and tau 1. If my test statistics is such that the separation between these two peaks are maximized, and also if the individual distributions are narrow enough, if this is very narrow, then the extent of overlap will be less with the other things. And again, this is also, if this is narrow, then the extent of overlap of this green curve with this would be again very same. So I am trying to reduce my sigma 0 square and sigma 1 square. All right. So my goal, is to increase the magnitude of this. So number one goal is to increase the magnitude of this. And number two is to decrease sigma 0 and sigma 1. Okay. If I can construct something that is uh, that achieves this goal, then it will perform my job very well. Okay, this will be perfect for my studies. All right. Okay. So then, if I construct a quantity that I call J, that is defined as tau 0 minus tau 1 square divided by sigma 0 square plus sigma 1 square. Notice this is a dimensionless thing because the dimension in upstairs and downstairs cancel each other. And if you try to maximize J, if you want to maximize J, then you kind of achieve both. You try to increase this tau 0 minus tau 1 whole square, and you try to decrease this thing. So it has the feature, it has both the feature that I need so that this T will be a good test statistic. And what this J will depend on? This J will depend on this A matrices. Because my tau alpha and sigma alpha square, they depend on this A matrices. These coefficients are precisely those things that I want to determine for my optimal test statistic construction. Okay. So basically, this J is a function of this A vector, coefficient of this thing. So you treat A as a parameter and you maximize this quantity J, and by maximizing you find out the value of this A vector and you substitute it in this test statistic, and that would be your optimal linear test statistic. That is the best test statistic that you can construct. No question about that. Okay, that is the best test. So this, if you construct your test statistic in this way, this particular linear test statistic is called the Fisher discriminant. Okay, so this is called the Fisher discriminant because it was Fisher who came up with this strategy of constructing a test statistic that can distinguish between data this way. Now again, my crucial assumption at the starting point of this discussion was that I have assumed my test statistic to depend linearly on data. Okay. They do not have a more complicated dependence on this xi. But you might ask, instead of choosing a linear discriminant or a linear test statistic, maybe we could choose a more complicated, a more sophisticated test statistic that kind of wiggles around this thing, okay? like this, maybe this, okay? And if so, look at this orange line. So this is definitely a non-linear function of x1 and x2. And if we could construct this kind of wiggly line, of course, this wiggly line will be more efficient than my simple linear one. Okay, but if I can construct this, then this would be a more efficient test statistic than a linear one. It's given. But to construct such a test statistic is again a non-trivial job. Okay, so remember, there is always a trade-off between how complicated you want your test statistic to be. So you're basically, the whole job of your test statistic is that how well it can separate data. Okay, Now, why do you want to separate data? Because you want to have your the purity of the sample to be increasing. So something like this you want to construct. You want to only have signal, and you want to reduce your background. Okay, that is the job you are doing. So if your pions are background, then you only want to have electrons. Now, suppose doing a linear test statistic, you get a purity of a sample of say 90%. Okay, and of course, you can improve the purity, you can improve the selection efficiency by choosing a nonlinear test statistic. And suppose the increase of purity gain from 90% for a linear for the linear test statistic to a nonlinear test statistic is just, let's say it becomes 92%, but it takes a huge toll on your computational efficiency. Okay? So remember, whenever you are choosing a test statistic, uh, then you have to consider the fact the gain as a result of choosing a more complicated nonlinear test statistic. Is it worth it? Is it worth the computational efficiency and the computational time that you are devoting yourself into? Is it worth it? Okay. That being said, however, there are certain fields where this 1% or 2% increase in purity makes, let's say, substantial impact, so that uh, the pain of moving from this linear test statistic to a non-linear one is worth it. Okay, and the constructing a nonlinear test statistic like this that basically trains your data in a better way is again a non-trivial business. And again, I will not discuss it because I have a limited knowledge and I do not know how to like uh, um, make it available in a classroom setting with limited computational power. But there are two very popular ways of constructing nonlinear test statistic. One is called ANN, or artificial neural networks. Okay, or rather, if you remove this artificial, is just neural networks. And then you have the option of boosted decision trees. So all these are algorithms, basically well written, well tested algorithm. Their sole job is to sample data. Okay, you have two different hypotheses, or there can be more than two hypotheses. In the simple case, I am considering just two hypotheses. There can be more than two hypotheses, not infinite, but usually a finite number of hypotheses. And their job is to construct one or more number of this nonlinear test statistic, using which they can make a trained and informed decision. Okay, and I will not discuss this neural network and boosted decision trees in this class again. But if you are interested in um, many of your research, you might need this. But at least you got the basic what do these things do. So what is the importance of studying neural network or boosted decision trees? Your beginner steps start from the need to sample data. Okay, and so these originated from the need of sampling data, and you now have a better understanding of what does sampling of data means. Okay. Now it would be very nice if at least one of you, or maybe all of you as a team, can go to the internet, find out such a distributed data, like say, let's say in a two-dimensional data to start with, let's say two-dimensional data. Okay, and you will find many such data. It can be data of anything, maybe electron pion, maybe it's available in the internet, maybe uh, whatever kind of data this is. Just take that data, write a program, and then try to construct a test statistic, and try to separate out these two hypotheses, whatever those two hypotheses are, and then calculate the purity of your sample and see how efficient is your sampling algorithm. Okay, and basically it's a test on how to write such an algorithm. By the way, I have never written such an algorithm. I never needed to, but this is an interesting exercise that if at least people who are associated with the experiment can give an example of a data and then write following this algorithm from scratch. Do not use any inbuilt sampling algorithm from your root or whatever. You write from scratch like this, okay, and then make it work. Okay? It will be very nice. Then we can do this in the next class. We can display this in the next class. Okay. So with this note, I will stop and I can now take a few questions if you have any. Any questions? Can someone volunteer to do this sampling of data in the next class? At least people with experimental background dig out an experimental set of data and then uh, demonstrate to everyone how this sampling is done.
Sir, can you repeat the question again, matlab clearly? Again.
Uh, so what I want you to do is that I gave you this plot of x1, x2, right? So you find a plot like that or some data like that. Suppose, so in general, in particle physics experiment, you have signal and background, right? And you have to separate signal from your background.
Yes, sir.
Okay. So there will be several data, let's say Jepsi data. Okay.
Okay.
When you are discovering a Jepsi, there would be a so Jepsi decaying into 2 electrons, right?
Yes.
So and 2 electrons can also come from Drelian and so on and so forth when you are doing E plus solution. Okay.
Mm.
So there is a irreducible background there, and on top you want to see Jepsi. Now you have to construct a test statistic that filters your Jepsi events compared to the E plus E minus just background, and then plot the signal events only.
Okay, sir.
Will you be able to do that?
Sir, I will try.
Okay, so we can try. We can try to see what happens. Okay, so nice. Thanks, Bhagarathi. Anyone else who would be able to do such a thing? All right then. So then let me stop recording here.